Welcome, folks. I want to give a part 2 on principal component analysis. So imagine you have a large data set of faces, images of faces. Each image you could maybe think of as a point in 10,000 dimensional space, just because you have 10,000 pixels. Okay, and you store a number for each pixel in this photo. And you can realign, those pixels to form a vector to really think of a face as a single vector or point in 10,000 dimensional space. PCA is related to things like, well, how might you represent this face as best as you can with less information? So instead of storing the value of every pixel, is there a better basis that with only a couple coefficients in that basis, you can still get a reasonable image that if your Wi-Fi is slow, you could still get a loose idea of who you're looking at and in which way they're looking. Okay, so let me place these faces and these blurry reconstructions on our schematics of principal component analysis. So here we're living in 10,000 dimensional space, or however high dimensional our data is. Maybe it just looks like 3D or even 2D to you right now. When you do PCA, and each data point is a face. So this data point might be that face, this data point might be that face, and this data point might be that face. Maybe this data point is this face right here. When you do PCA, you find a linear model of best fit. And in this picture, I've just found a line as my model, but you certainly could consider planar models. Oh, let's draw that a little bit better. You could consider planar models, or in 10,000 dimensional space, you could consider a model that's a 3-dimensional vector space, or a 4-dimensional vector space, or 5-dimensional vector space. Once you find that model, you can project the data points down onto that model. So map each face to the closest point on your model. And then once you projected things, that's when you get these blurry faces, okay? So these blurry faces are your projected data points. So you didn't project the data points because you wanted to make them blurry. You projected them because you wanted to store them in a more efficient way. So the eigenfaces correspond to, the directions used when building this model. So this eigenface, this ghost picture, let me outline it in red, corresponds to this basis vector, telling you what is the direction in which your linear model is pointing, okay? And if we had a 2D representation of our PCA model, right, we'd also have another vector pointing in that direction of the plane. And so you have another eigenface basis vector corresponding to that direction. Okay. So the eigenfaces don't look like actual people. They look like these ghosts, but they're ghosts that are well designed to add together in order to produce good representations of people. So in this 1D model, right, every data point has been written as a single scalar multiple of that red eigenface. I mean, in practice, these are combinations of many different eigenfaces. So, in practice, these blurry faces, are sums not only of the red eigenface, but also of this purple eigenface, and tens or maybe even hundreds more eigenfaces. Okay, but you don't need nearly 10,000 eigenfaces to produce these images. You only need on the order of roughly, I think, 100 or maybe 1,000 faces, which is still a lot less than 10,000. So the reason why these spaces are blurry is because they live exactly in this low dimensional planar model. They're precisely equal to some number of this ghost plus some number of this ghost. Different numbers for different images that you're trying to reconstruct, but it's very low dimensional. If we use 10 ghosts in this model, if we have a projection down to 10D space, then in some sense you're storing this blurry face as only 10 numbers, the coefficients with respect to 10 different ghosts, as opposed to all 10,000 pixel values. Public questions.
So I guess one key part of this then is that you need to also store all of the ghosts. So this sort of becomes efficient really when you're storing a bunch of faces.
That's a really good point. Yeah, the ghosts are a good model for many different faces. But yeah, you know, if you were trying to load a web page more quickly, right, you would need these ghosts already sort of downloaded to your computer. Other public questions or comments? And I should say, I don't know if exactly PCA is used in downloaded faces from the computer. I think it's not, you know, things like the JPEG standard are what used, but this is a good analogy for what's going on in principal component analysis. Thanks so much.